Picture this. As you watch this video, scientists now believe they may have uncovered a clue, one hidden in the structure of space-time itself, that suggests we might be living inside something far stranger than we ever imagined. A clue that points not just to a cosmic mystery, but to a possibility long whispered about in theoretical physics. Imagine if every breath you take, every step you have ever walked, every moment of human history has unfolded within the event horizon of a black hole so vast that our entire observable universe floats inside it like a dust particle. Unthinkable, right? And yet, recent analyses of Einstein equations combined with new insights into black hole interiors, cosmic expansion, and the behavior of space-time have led some physicists to an unsettling conclusion. The universe behaves exactly like the inside of a black hole, not metaphorically, not poetically, mathematically. The most unnerving part? The deeper researchers look, the harder it becomes to rule it out. If you love the content, leave a like and subscribe to the channel, as today we're diving deep into one of the most provocative and bizarre hypotheses in all of cosmology. Let us start. Part 1. The Black Hole Enigma. Black holes weren't always a part of our scientific understanding. In fact, when the concept first emerged from the equations of general relativity, even Albert Einstein himself was deeply skeptical that such bizarre objects could actually exist in nature. The story of black holes is really the story of gravity taken to its most extreme logical conclusion, where the fundamental fabric of space and time itself becomes so warped that reality as we understand it ceases to function normally. To truly grasp what a black hole is, we need to travel back over a century to when Einstein revolutionized our understanding of gravity itself. Before Einstein, gravity was understood through Newton's elegant but ultimately incomplete theory. Newton described gravity as a force that acted instantaneously across any distance, pulling objects together with a strength determined by their masses and the distance between them. This worked brilliantly for predicting planetary orbits and falling apples, but it left fundamental questions unanswered. How did gravity actually work? How could the Sun instantaneously pull on the Earth across 93 million miles of empty space? And perhaps most troublingly, Newton's equations predicted that gravity should act infinitely fast, which violated emerging principles about the speed of light being the universe's ultimate speed limit. Einstein's 1915 general theory of relativity provided a radical new answer. Gravity, Einstein proposed, wasn't a force at all. Instead, it was the result of mass and energy warping the fabric of space-time itself. Imagine space-time as a vast, flexible sheet. Place a heavy object on this sheet, and it creates a depression, a curve in the fabric. Other objects moving nearby don't feel a mysterious force pulling them toward the heavy object. Instead, they're simply following the natural curves in space-time, rolling along the depression like marbles circling a funnel. This wasn't just a metaphor. Einstein showed that space and time themselves were physically distorted by the presence of matter and energy. The equations that emerged from this insight, known as the Einstein field equations, were staggeringly complex. They described how matter and energy tell space-time how to curve, and how that curvature tells matter and energy how to move. These equations have passed every experimental test we've thrown at them for over a century. They predicted the bending of starlight around the Sun, observed during the famous 1919 solar eclipse expedition that made Einstein a household name. They predicted the precise rate at which time runs slower in stronger gravitational fields, a phenomenon now routinely measured by GPS satellites and atomic clocks. They predicted gravitational waves, ripples in space-time itself, which were finally directly detected in 2015, exactly a century after Einstein published his theory. General relativity has been ridiculously, almost absurdly successful. It's one of the two pillars of modern physics, alongside quantum mechanics, and it's never failed a single experimental test. But here's the problem, and it's a big one. Einstein's beautiful equations contain within them the seeds of their own destruction. There are specific situations, specific configurations of matter and space-time where the mathematics breaks down completely, spitting out infinities and nonsensical predictions. Physicists call these breakdowns singularities, and they represent the places where general relativity must be replaced by some deeper theory we don't yet have. And wouldn't you know it, singularities show up in exactly two places that are central to our story: at the centers of black holes and at the Big Bang itself. To understand how black holes form, we need to understand stellar death. Stars are vast nuclear furnaces, fusing hydrogen into helium and releasing enormous amounts of energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. For most of a star's life, it exists in a delicate equilibrium, with gravity trying to crush it inward and nuclear fusion pushing outward. But nuclear fuel doesn't last forever. Eventually, stars run out of fuel, and when they do, that outward pressure vanishes. Gravity wins. For smaller stars like our Sun, this collapse is relatively gentle. The star puffs off its outer layers and the core compresses into a white dwarf, an incredibly dense object about the size of Earth but with the mass of the Sun. The electrons in the white dwarf's matter resist being compressed further through a quantum mechanical effect called electron degeneracy pressure, and this stabilizes the star. But for stars much larger than the Sun, something far more dramatic happens. When a massive star exhausts its nuclear fuel, it undergoes catastrophic collapse. The core implodes in a fraction of a second, and the outer layers explode in a supernova, one of the most violent events in the universe. What's left behind depends on the mass of the core. If it's not too massive, it becomes a neutron star, where gravity is strong enough to overcome electron degeneracy pressure and crush protons and electrons together into neutrons. Neutron stars are even denser than white dwarfs, packing more mass than the Sun into a sphere just 10 miles across. But neutrons also resist being compressed through neutron degeneracy pressure. This can stabilize the remnant, at least if it's not too massive. But if the stellar core is massive enough, nothing can stop the collapse. No known force in physics is strong enough to resist gravity's inward pull. The core keeps shrinking, growing denser and denser. According to general relativity, this collapse doesn't stop. The matter falls inward until it's compressed to infinite density at a single point, a singularity. And as this happens, something extraordinary occurs in the space-time surrounding the collapsing matter. As matter collapses toward infinite density, the warping of space-time around it becomes more and more extreme. At some critical radius, something remarkable happens. The curvature becomes so severe that space-time itself begins flowing inward faster than the speed of light. This is the event horizon, and it's one of the most profoundly important concepts in all of black hole physics. Think about space-time as being like a flowing river. In flat, empty space, far from any massive objects, the river is calm and still. You can swim in any direction you like. But near a massive object, space-time begins to flow, pulled along by the warping of gravity. Near the Earth, this flow is gentle, barely noticeable. Near a neutron star, it's more significant, but you could still, in principle, swim against it if you had powerful enough engines. But at the event horizon of a black hole, the flow reaches the speed of light itself. This creates a one-way boundary in space-time. Anything that crosses the event horizon from outside is swept inexorably inward by the flow of space-time itself. There's no escape, not because you can't move fast enough, but because every direction you could possibly move, even at the speed of light, points inward. The event horizon isn't a physical surface made of matter or energy, it's a mathematical boundary, a point of no return in the structure of space-time itself. From the outside, it appears as a sphere of absolute darkness, because no light that crosses it can ever return to tell us what lies within. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers in radius. For a supermassive black hole with 1 billion times the mass of the Sun, like those found at the centers of galaxies, the event horizon could be larger than our entire solar system. But no matter the size, the defining feature is the same. Cross it, and you can never come back. Inside the event horizon, things get even stranger. In our everyday experience, space and time play very different roles. We can move freely through space in any direction, forward, backward, left, right, up or down. But time flows in only one direction, relentlessly forward. Once you cross the event horizon, this distinction breaks down in the most disturbing way imaginable. The direction toward the singularity becomes time-like, meaning that approaching the singularity becomes as inevitable as moving forward in time. Just as you cannot stop aging, cannot stop time from carrying you into the future, once inside a black hole, you cannot stop yourself from reaching the singularity. It's not in a particular direction in space that you can avoid. It's in your future, as unavoidable as tomorrow. At the center of every black hole, according to general relativity, lies a singularity. This is where all the infalling matter ends up, compressed to literally infinite density at a single point. It's where the curvature of space-time becomes infinite, and where the equations of general relativity break down completely. Physicists hate singularities because they represent the failure of our theories. When your equations give you infinity as an answer, it's nature's way of telling you that you're asking a question your theory can't answer. The singularity is where quantum mechanics and general relativity come into irreconcilable conflict. General relativity describes gravity and the large-scale structure of space-time, but it completely ignores quantum mechanics, the physics of the very small. Quantum mechanics, meanwhile, treats space-time as a fixed background and ignores the fact that space-time itself can be dynamic and curved. In most situations, this doesn't matter. Quantum effects are important at tiny scales, gravity is important at large scales, and the two rarely interact. But at a singularity, you have an enormous amount of mass compressed into a quantum scale region. Both quantum mechanics and general relativity should be important, but we don't have a theory that combines them. This is the holy grail of theoretical physics, a theory of quantum gravity that would describe what really happens at the center of black holes and at the Big Bang. String theory, loop quantum gravity, and various other approaches have been proposed, but none are complete or experimentally verified. Until we have such a theory, the singularity remains a mystery, a marker on the map of physics that says, "Here be dragons, our current understanding ends here." But here's something fascinating. The existence of singularities in general relativity tells us something profound. It tells us exactly where our best theory of gravity fails. And as we'll see, the fact that black hole singularities and the Big Bang singularity are both places where general relativity breaks down turns out to be more than just a coincidence. The mathematical similarities between these two types of singularities are what open the door to the possibility that our universe might actually be inside a black hole. Part 2. the Big Bang and cosmic horizons. Just as black holes contain a singularity at their center, our universe contains a singularity in its past. We call it the Big Bang. This wasn't an explosion in space, but rather the explosive expansion of space itself, emerging from a state of infinite density and temperature some 13.8 billion years ago. Just like the black hole singularity, the Big Bang represents a breakdown of general relativity, a point where the equations cease to make sense and we need a theory of quantum gravity to describe what really happened. The evidence for the Big Bang is overwhelming. Everywhere we look in the universe, galaxies are moving away from us, and the farther away they are, the faster they're receding. This isn't because they're moving through space away from us. Rather, space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. When we look at distant galaxies, we're looking back in time, seeing them as they were billions of years ago when their light began its journey to us. And the farther back we look, the closer together everything was. Trace this expansion backward far enough, and you reach a point about 13.8 billion years ago, when all the matter and energy in the observable universe was compressed into an unimaginably hot, dense state. We can actually see the afterglow of the Big Bang. The cosmic microwave background radiation is light that has been traveling through space for over 13.8 billion years, released when the universe was just 380,000 years old and cool enough for atoms to form. This light fills all of space, coming at us from every direction, and it carries the imprint of conditions in the early universe. Its spectrum is almost perfectly thermal, matching what we'd expect from a hot, dense early universe, and its tiny variations tell us about the density fluctuations that eventually grew into galaxies and galaxy clusters. But the Big Bang singularity itself, the moment of infinite density, remains mysterious. Was there truly a singularity, or does quantum gravity smooth it out into something else? We don't know. What we do know is that the observable universe emerged from an extremely hot, dense, rapidly expanding state, and that tracing backward, general relativity predicts a singularity where all the familiar laws of physics break down. Sound familiar? It should, because it's exactly what happens at the center of a black hole. Here's where things start to get really interesting. Our universe doesn't just have a singularity in its past. It also has an event horizon, though it's quite different from a black hole's event horizon. This is called the cosmological event horizon, and it exists because space itself is expanding. When we say space is expanding, we mean that distant objects are moving away from us, and the farther away they are, the faster they're receding. This is described by Hubble's law. The recession velocity of a galaxy is proportional to its distance from us. Double the distance, double the recession velocity. Keep going far enough, and eventually you reach distances where the recession velocity equals the speed of light. Beyond that distance, recession is faster than light speed. Now, before you object that nothing can move faster than light, remember that this isn't objects moving through space, but space itself expanding and carrying objects with it. There's no law of physics that says space itself can't expand faster than light. What this means is profound. There are regions of the universe that are moving away from us faster than light. Events happening there right now can never influence us, because any signal they send would be fighting against the expansion of space itself and losing, like a swimmer trying to swim upstream in a current faster than they can swim. The boundary between regions that can influence us and regions that cannot is the cosmological event horizon. Now, there's an important subtlety here. We can actually see galaxies that are currently beyond our cosmological event horizon. How is that possible? Because the light we're seeing from them was emitted long ago, when those galaxies were closer to us and still within our observable region. That light has been traveling toward us for billions of years, and even though the galaxy that emitted it has been carried beyond our horizon by the expansion of space, the light made it across before that happened. But any light emitted from those galaxies now, any events happening there today, will never reach us. There's another complication too. The expansion of space isn't just continuing at a constant rate, it's actually accelerating. This acceleration, driven by something we call dark energy that we don't really understand, means that the cosmological event horizon is closer to us than you might naively expect. As time goes on and the acceleration continues, fewer and fewer distant objects remain within our future light cone, the region of space-time that can send us signals. The net effect is that we live in a universe with a clear boundary on what we can observe and what can influence us. There is a surface at a finite distance, our cosmological event horizon, beyond which events are forever unknowable to us. This surface shares a crucial property with a black hole's event horizon. It's a one-way boundary in space-time that limits what regions can communicate with other regions. In the black hole case, the boundary prevents things inside from getting out. In the cosmological case, the boundary prevents things outside from getting in. Let's step back and compare what we've learned about black holes and the universe. A black hole has a singularity at its center where matter is crushed to infinite density and the laws of physics break down. Our universe has a singularity in its past, the Big Bang, where matter was compressed to infinite density and the laws of physics break down. A black hole has an event horizon, a one-way boundary that things can cross from outside to inside, but never from inside to outside. Our universe has a cosmological event horizon, a boundary beyond which events can never influence us. The similarities are striking, but there also seem to be crucial differences. The black hole singularity appears to us as a point of infinite density in space, located at the center of the black hole. The Big Bang singularity was a moment of infinite density that included all of space, happening everywhere at once in the past. The black hole's event horizon is a surface in space that you can approach, cross, and move away from its center. The cosmological event horizon is a distant scale that defines how far away things can be and still influence us. Black holes are localized objects embedded in the larger universe. The universe is, well, everything, with no outside to be embedded in. These differences seem fundamental. How could we possibly reconcile them? How could something localized in space like a black hole be equivalent to the entire universe? The answer lies in one of the most subtle and profound aspects of general relativity. The relationship between space and time can change depending on the curvature of space-time, and in particular, the distinction between the black hole singularity being a place and the Big Bang being a time turns out to be less fundamental than it first appears. Part 3: Geodesics and Singularities. To understand how black hole singularities and the Big Bang can be more similar than they first appear, we need to introduce a crucial concept from general relativity: geodesics. A geodesic is the straightest possible path through curved space-time. In flat space, geodesics are just straight lines, but in curved space-time, geodesics curve along with the geometry. When you throw a ball, it follows a geodesic through space-time, tracing out a parabolic arc. The Moon orbits Earth on a geodesic, following the straightest path it can through the curved space-time around our planet. In fact, geodesics are fundamental to how we define the structure of space-time itself. You can think of geodesics as forming a kind of grid that maps out the fabric of space-time. At any point in space and time, you can define geodesics pointing in different directions, some primarily spatial and some primarily temporal, and these geodesics collectively define the geometry. Objects that aren't being pushed or pulled by any forces naturally follow geodesics, which is why we say they follow straight lines through curved space-time even when their paths appear curved to us. Here's the important part. Geodesics can be traced forward and backward through time. If you have a geodesic defined at some particular moment, you can extend it into the future to see where it will go, and you can extend it into the past to see where it came from. For example, consider the geodesic that describes the path of a ball thrown through the air. You can trace this geodesic forward to predict where the ball will land, but you can also trace it backward to see what trajectory would have brought the ball to its current position. You could even extend it backward through the ground, finding the path through the earth that this geodesic follows, even though the ball never actually travelled that path. In a generic space-time, geodesics extend infinitely into the past and future. Pick any geodesic and trace it backward, and it just keeps going, back through earlier and earlier times, forever. Trace it forward, and it continues into the infinite future. This is called geodesic completeness. But there are situations in general relativity where geodesics don't extend forever. There are places where geodesics simply end or begin with no earlier or later extension possible. These endpoints are singularities. In general relativity, a singularity is formally defined as a boundary where geodesics end. The Big Bang is a singularity because all geodesics in our universe, when traced backward in time, terminate at the Big Bang. You can follow any trajectory backward, any possible path that anything could have taken, and they all converge on a point about 13.8 billion years ago. Before that, the geodesics simply don't exist. It's not that we don't know what happened before the Big Bang, it's that before may not be a meaningful concept. Time itself may have begun at the Big Bang. This leads to a crucial insight about what kind of singularity the Big Bang is. It's a past singularity, meaning it's where geodesics end when traced backward in time. But it's also space-like, meaning it encompasses all of space at a single moment. The Big Bang didn't happen at a particular location in space. It happened everywhere at once. Every point in the universe shares the same Big Bang singularity in its past. The entire spatial universe emerges from this single moment of infinite density. Now let's think about a black hole. The singularity at the center of a black hole is also a place where geodesics terminate. But here's the twist. They terminate in the future, not the past. Once you cross the event horizon of a black hole, all geodesics, all possible paths you could follow, end at the singularity. And they don't end at different times. From the perspective of someone falling into the black hole, all paths reach the singularity at the same moment. The singularity is not a point at the center of the black hole that you approach. It's a moment in your future, an instant that all possible paths lead to. This is incredibly difficult to visualize because our intuitions about space and time break down inside the event horizon. Outside the black hole, the singularity appears to be at the center, a location in space. But once you cross the horizon, the character of the singularity changes. It's no longer ahead of you in space. It's in your future in time. Just as every moment of your life is followed by another moment carrying you forward in time, every moment inside the black hole is followed by another moment carrying you toward the singularity. The black hole singularity is called a future, space-like singularity. Future because it lies in the future of all geodesics that reach it. Space-like because, just as the Big Bang singularity was spread across all of space at a single moment, the black hole singularity is spread across all of the black hole space at a single moment in the future. From inside the black hole, the singularity is everywhere, the same way the Big Bang was everywhere when viewed from our universe. This is where the deep similarity between black holes and the universe starts to emerge. The Big Bang is a past, space-like singularity. All points in space share this singularity in their past. All geodesics in the universe originate from it. The black hole singularity is a future, space-like singularity. All points inside the event horizon share this singularity in their future. All geodesics within the black hole terminate at it. The primary difference between them is just a matter of time direction. The Big Bang is where space-time begins. The black hole singularity is where space-time ends. The Big Bang is the universal past. The black hole singularity is the universal future, at least for the region inside the event horizon. But mathematically, they're describing very similar structures. They're both space-like singularities where geodesics terminate and the equations of general relativity break down. Now you might be thinking, wait, doesn't that mean I'm doomed to eventually fall into the black hole singularity at the center of our galaxy? No, and here's why. The black hole singularity is only in the future of geodesics that lie within the event horizon. The space-time inside a black hole is disconnected from the space-time outside. If you're outside the event horizon, geodesics in your region of space-time don't lead to the black hole's singularity. The singularity is only the universal future for the distinct space-time that exists inside the horizon. It's a separate, causally disconnected region of space-time. This is crucial for understanding what it would mean for our universe to be inside a black hole. The interior of a black hole is its own domain of space-time with its own singularities. For someone inside, the singularity in their future is the end of their space-time. For someone outside, that singularity doesn't affect them at all. They live in a different region of space-time with different geodesics and different singularities. So we've established that black holes and the universe both have space-like singularities, just facing opposite time directions. We've established that both have event horizons that create causal boundaries. But there's still a glaring difference. Black holes are objects embedded in a larger universe, with an inside and an outside. The universe isn't embedded in anything larger. It's everything. To really make the case that our universe could be a black hole, we need to eliminate that difference. We need to create a black hole with no outside. Part 4. White holes and time reversal. Einstein's equations have a beautiful property called time reversal symmetry. If you have a solution to Einstein's equations, you can flip the direction of time, turning future into past and past into future, and you'll get another valid solution. For a black hole, what happens when you reverse time? You get something called a white hole. A white hole is exactly what it sounds like, the time-reversed version of a black hole. While a black hole has a future singularity that everything inside is doomed to reach, a white hole has a past singularity from which everything emerges. While a black hole's event horizon can only be crossed from outside to inside, a white hole's event horizon can only be crossed from inside to outside. Nothing can enter a white hole from outside, but things can emerge from within. Think of it this way. Imagine watching a video of matter falling into a black hole, swirling around the event horizon before crossing and disappearing inside, eventually reaching the singularity. Now play that video in reverse. You'd see matter emerging from the singularity, traveling outward, crossing the event horizon from inside to outside, and then streaming away into space. That's a white hole. It's a region of space-time with a past singularity, surrounded by an event horizon that acts like a one-way boundary in the opposite direction from a black hole. From the outside, a white hole would appear as a bright source, continuously emitting matter and energy from a localized region in space. Inside the white hole, space-time flows outward at the speed of light across the event horizon. Just as nothing can escape from inside a black hole because space-time flows inward faster than light, nothing can enter a white hole because space-time flows outward faster than light. Any matter or light that tries to approach from outside is swept away by this outward flow. White holes are perfectly valid solutions to Einstein's equations. Mathematically, they're just as legitimate as black holes. The question is whether they actually exist in nature. And here's where things get interesting from a cosmological perspective. Because a white hole has a past singularity and an event horizon that can't be crossed from outside, it shares crucial features with our universe. Our universe has a past singularity, the Big Bang, and an event horizon, the cosmological horizon, beyond which events can't reach us. Could our universe actually be the interior of a white hole? At first glance, this seems absurd. The interior of a white hole, as originally conceived, looks nothing like our universe. The original white hole solution came from mathematically manipulating the Schwarzschild solution, the simplest possible black hole solution discovered by Carl Schwarzschild in 1916. This solution describes a perfectly spherical, non-rotating black hole of constant mass, existing eternally. When you manipulate the mathematics to extend this solution, you get all sorts of weird structures including white holes, wormholes, and parallel universes connected through the black hole's interior. We've explored these mathematical extensions before, and they describe spacetimes that are wildly different from what we observe. The Schwarzschild white hole has several properties that make it a terrible match for our universe. First, it contains no matter. The Schwarzschild solution is a vacuum solution, meaning it describes empty curved spacetime with no matter or energy present. Our universe, obviously, is full of matter and energy, from stars and galaxies to dark matter and dark energy. Second, the interior of a Schwarzschild white hole is highly inhomogeneous. The curvature of spacetime changes dramatically as you move through it, particularly as you approach the singularity. This would create extreme tidal forces that would stretch and squeeze anything traveling through it. Our universe, by contrast, is remarkably homogeneous. When we look at the universe on the larger scales, matter and energy are distributed very evenly. The cosmic microwave background shows us that the early universe was even more homogeneous, with density variations of only about 1 part in 100,000. And crucially, spacetime in our universe is very nearly flat. The geometry we observe is extraordinarily close to Euclidean geometry, with minimal curvature. This is called the flatness problem, and it's one of the motivations for cosmic inflation, but that's a story for another time. The point is that our universe shows none of the extreme curvature and inhomogeneity that you'd expect inside a simple Schwarzschild white hole. So if we're going to argue that our universe is inside a white hole, we need a very different kind of white hole from the simple Schwarzschild solution. We need a white hole interior that is homogeneous, filled with matter and nearly flat. Does such a solution exist in general relativity? Remarkably, yes. And the path to finding it goes through one of the first realistic models of black hole formation ever developed. Part 5. The Oppenheimer-Snyder solution. In 1939, J. Robert Oppenheimer, who would later become famous as the scientific director of the Manhattan Project, was working on understanding stellar collapse with his graduate student, Hartland Snyder. They wanted to model what happens when a massive star exhausts its nuclear fuel and collapses under its own gravity. This was years before anyone had any idea what a black hole really was. The term black hole itself wouldn't be coined until 1967 by John Wheeler. But Oppenheimer and Snyder were exploring the mathematics of complete gravitational collapse, where nothing could stop matter from compressing indefinitely. To make the problem tractable, they made some dramatic simplifications. They modeled the collapsing star as a perfectly uniform sphere of matter with absolutely no pressure. Real stars, of course, have pressure gradients. They're denser at the center than at the surface, and the pressure of the hot gas inside supports the star against gravity. But Oppenheimer and Snyder wanted the simplest possible model that would capture the essence of collapse, so they stripped away these complications. What they found was remarkable. As this uniform, pressureless sphere of matter collapses, an event horizon forms around it. From the outside, an observer would see the surface of the sphere slow down as it approached the radius that would become the event horizon, never quite seeing it cross. Light from the surface would become increasingly redshifted, making the collapsing object appear to dim and redden, asymptotically approaching invisibility. This was our first mathematical glimpse of what we now call a black hole. But the really interesting part was what happens inside. Despite the formation of an event horizon, the interior of the collapsing star remained remarkably simple. The matter continued to collapse uniformly, with every part of the sphere maintaining the same density as every other part. There were no tidal forces stretching and squeezing the matter, at least not until the very end when the matter approached the singularity. The space-time geometry inside the collapsing star remained flat, or very nearly so, until the final moments of collapse. Now here's the crucial insight. The assumptions Oppenheimer and Snyder made about the collapsing star, uniform density and zero pressure, are exactly the same assumptions that Alexander Friedmann made when he first solved Einstein's equations for the entire universe back in 1922. Friedmann was looking for cosmological solutions, models that could describe the universe as a whole. He assumed, as a simplification, that matter in the universe was perfectly uniformly distributed and had no pressure. These assumptions led him to discover what we now call the Friedmann equations, which describe an expanding or contracting universe. The solutions Friedmann found are described by what's called the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW metric for short. This metric describes a homogeneous isotropic universe, meaning it looks the same at every point and in every direction. It's the standard model for cosmology, the mathematical framework we use to describe the expanding universe we observe. And here's the kicker. The space-time inside the Oppenheimer-Snyder collapsing star is described by exactly this same FLRW metric. What Oppenheimer and Snyder showed is that you can take a black hole solution, the Schwarzschild metric that describes the curved space-time outside the collapsing star, and patch it together with an FLRW cosmological metric that describes the space-time inside. The boundary between these two regions is the surface of the collapsing star itself. Outside, space-time is curved according to Schwarzschild's solution, with an event horizon forming at a particular radius. Inside, space-time is described by the FLRW metric, the same metric we use to describe our entire universe. This is profound. It means that the interior of this particular kind of black hole looks like a small universe unto itself. It's homogeneous, with matter uniformly distributed. It's described by the same mathematics we use for cosmology. And most importantly, an observer inside this region, inside the event horizon, but still surrounded by the collapsing matter, would experience space-time very differently from what you'd expect inside a typical black hole. Remember, in a simple Schwarzschild black hole, once you cross the event horizon, The singularity is in your future and you experience extreme tidal forces as you approach it. But inside the Oppenheimer-Snyder collapsing star, things are gentler. The space-time remains flat, or nearly flat. The singularity is still in your future, but it's not a localized point that you fall toward. Instead, it's more like a moment in time that all of space is approaching together, much like how all of space in our universe emerged from the Big Bang. Now, the Oppenheimer-Snyder solution describes a collapsing star, matter falling inward toward a future singularity. But remember our discussion of white holes? If we can time reverse a black hole to get a white hole, we can time reverse the Oppenheimer-Snyder solution too. Instead of a uniform sphere of matter collapsing inward through an event horizon toward a singularity in the future, we'd have a uniform sphere of matter expanding outward from a singularity in the past, through an event horizon into the surrounding space. And here's where it gets beautiful. The interior of this time-reversed solution would still be described by an FLRW metric. But now, instead of a contracting FLRW universe, it would be an expanding one. Instead of matter collapsing toward a future singularity, matter would be expanding away from a past singularity. Does this sound familiar? It should. It's exactly what our universe does. We live in an expanding FLRW universe that emerged from a past singularity called the Big Bang. So here's what we have: a white hole solution where the interior is described by an expanding FLRW cosmology, the same cosmology that describes our universe. From inside this white hole, you would observe matter uniformly distributed, expanding away from a past singularity, with flat or nearly flat space-time geometry. There would be an event horizon, but it would be far enough away, and the universe inside would be large enough that you might never notice it. From the outside, this object would look like a white hole, a bright region of space that nothing can enter, continuously emitting matter and radiation. But from the inside, it would look like an entire universe, with a Big Bang in the past and space expanding in all directions. An observer inside couldn't tell the difference between being in this white hole interior and being in a standalone universe, at least not without traveling to the edge and encountering the event horizon. This was the essential insight of Raj Pathria, an Indian physicist who proposed what he called black hole cosmology in 1972. Pathria argued that our universe could be the interior of an extremely large white hole, so large that the event horizon is far beyond our observable universe, and we've never encountered it. From our perspective, we see an expanding universe with a Big Bang in the past, and we have no way to determine whether we're in a standalone universe or inside a white hole embedded in some larger space-time. The beauty of this idea is that it explains both the singularity and the event horizon of our universe in one framework. The Big Bang becomes the past singularity of the white hole. The cosmological event horizon becomes related to the white hole's event horizon. And the homogeneity and flatness of our universe are natural consequences of being inside an Oppenheimer-Snyder type solution, where the interior is described by an FLRW metric. Now, you might object that we still have a problem. A white hole, even one with an FLRW interior, is still embedded in a larger space-time. There's still an outside to the white hole, a larger universe in which it exists. And that means our universe would be just a small bubble inside something bigger, which doesn't match our understanding that the universe is everything. But remember, we can only observe and interact with what's inside our event horizon. If there is something outside, some larger space-time that our white hole is embedded in, we could never know about it. It would be forever beyond our causal reach. Moreover, there's a way to make the distinction between white holes and black holes blur, which brings us to one of Stephen Hawking's most intriguing insights. Part 6. Hawking's unification. In the 1970s, Stephen Hawking made one of the most surprising discoveries in theoretical physics. He showed that black holes aren't entirely black, they emit radiation. This Hawking radiation, as it's now called, comes from quantum effects near the event horizon. The vacuum of empty space is not truly empty at the quantum level. Virtual particle-antiparticle pairs constantly pop into existence and annihilate each other, a phenomenon allowed by Heisenberg's uncertainty principle. Near the event horizon of a black hole, something remarkable can happen. One particle of the pair can fall into the black hole while the other escapes to infinity. To an outside observer, it looks like the black hole is emitting radiation. This radiation carries energy away from the black hole, which means the black hole is losing mass. Very slowly, to be sure, a stellar mass black hole would take longer than the current age of the universe to evaporate significantly via Hawking radiation. But in principle, over vast timescales, black holes can evaporate completely through this process. This discovery fundamentally changed our understanding of black holes, showing that they're not eternal, unchanging objects, but dynamic systems that can evolve and eventually disappear. But there's another aspect of Hawking radiation that's relevant to our story. The spectrum of Hawking radiation is thermal, meaning it has a temperature. This temperature is inversely proportional to the mass of the black hole. Bigger black holes are colder, smaller black holes are hotter. A stellar mass black hole has a temperature of only a few billionths of a degree above absolute zero. A supermassive black hole at the center of a galaxy is even colder. But here's the crucial point. This temperature means that black holes are not just emitting radiation, they can also absorb it. Any object with a temperature can come into thermal equilibrium with its environment. If the black hole is in an environment that's hotter than it is, it will absorb more radiation than it emits and grow. If the environment is cooler, it will emit more than it absorbs and shrink. In our current universe, there's a bath of radiation filling all of space, the cosmic microwave background, with a temperature of about 2.7 Kelvin. For any black hole larger than about the mass of the Moon, this background radiation is warmer than the Hawking temperature, so these black holes are currently growing, absorbing slightly more radiation than they emit. In 1999, Stephen Hawking explored a fascinating scenario. What if a black hole exists in perfect thermal equilibrium with its environment? Imagine a black hole whose Hawking temperature exactly matches the temperature of the surrounding radiation bath, so it absorbs radiation at exactly the same rate it emits it. The black hole's mass remains constant. It's neither growing nor shrinking. It's in a perfect steady state. Hawking showed that in this situation, something subtle but profound happens to the mathematics. The distinction between a black hole and a white hole becomes ambiguous. Remember, a black hole has a future singularity and an event horizon you can enter, but not exit. A white hole has a past singularity and an event horizon you can exit but not enter. But when a black hole is in perfect thermal equilibrium, emitting and absorbing radiation at the same rate, the time-directional distinction between past and future becomes less clear. Think about it this way. If the black hole is unchanging, in perfect equilibrium, then the physics looks the same whether you run time forward or backward. The black hole absorbs a photon, the photon disappears into the event horizon. Run this backward in time and the photon emerges from the event horizon, emitted by the black hole. But this is exactly what should happen given Hawking radiation. The time-reversed process and the time-forward process are both physically occurring at the same rate in equilibrium. In this state, you can't clearly distinguish whether you have a black hole that's emitting Hawking radiation or a white hole that's emitting its contents. The mathematical structures blur together. Hawking's argument was subtle and technical, but the implication was clear. In the right circumstances, black holes and white holes might not be distinct objects, but rather two aspects of the same thing, distinguished only by the time direction you choose to emphasize. This has profound implications for our question. If we're going to argue that our universe is inside a white hole, we need to deal with the fact that white holes seem unphysical in many ways. They require very special initial conditions, they're unstable in most scenarios, and we've never observed anything that looks like a white hole in nature. But if Hawking is right, and black holes and white holes can be the same object under the right conditions, then the apparent unphysicality of white holes becomes less of a problem. Let's now collect all the pieces and see what we can build. We have the Oppenheimer-Snyder solution showing that you can patch an FLRW cosmology inside a black hole, or by time reversal, inside a white hole. We have Pathria's observation that if such a white hole were large enough, observers inside couldn't distinguish it from a standalone universe. We have Hawking's insight that black holes and white holes can blur together under equilibrium conditions. And we have the mathematical similarities between the Big Bang singularity and black hole singularities, both being space-like singularities where geodesics terminate and general relativity breaks down. Combine all these ingredients and you get a picture, admittedly speculative and far from proven, where our universe could potentially be the interior of an extremely massive black hole existing in some larger parent universe. The Big Bang would be the singularity of this black hole. Our expansion would be the expansion of space inside the black hole's event horizon. The cosmological event horizon would be related to the black hole's event horizon, and the homogeneity and flatness we observe would be natural consequences of the FLRW metric describing the interior. From our perspective inside, we would see exactly what we do see: an expanding universe with a Big Bang in the past, uniform distribution of matter and energy, and a horizon beyond which we cannot observe. We would have no way to detect the outside universe in which our black hole exists, because we're inside the event horizon and causally disconnected from that exterior region. The mathematics of general relativity allows this scenario. Nothing in our observations rules it out. But does this mean we should believe we're in a black hole? Not necessarily. The standard cosmological model, where our universe is not embedded in any larger structure but is truly all there is, works perfectly well to explain everything we observe. The hypothesis that we're inside a black hole adds no explanatory power. It makes no testable predictions that differ from standard cosmology. It's consistent with general relativity and consistent with observations. But so is the simpler idea that our universe is just a universe, not the interior of something larger. This is an important distinction in science. An idea can be possible without being necessary. It can be consistent with the evidence without being supported by the evidence. Until someone finds a way to test the hypothesis, to make predictions that differ from standard cosmology and can be verified or falsified, it remains in the realm of interesting speculation rather than established science. That said, the fact that this idea emerges naturally from the mathematics of general relativity, requiring no exotic physics or modifications to Einstein's equations, makes it worth taking seriously as a logical possibility. Part 7. Cosmological Natural Selection. There's another fascinating twist on the idea of universes inside black holes, one that potentially gives the hypothesis more explanatory power. This is the idea of cosmological natural selection, proposed by physicist Lee Smolin. The core concept is that black holes don't form singularities, but instead bounce back, creating new expanding universes inside them. And this process happens every time a black hole forms, leading to a kind of cosmic reproduction where universes give birth to offspring universes through black holes. Here's how it works. In standard general relativity, the interior of a black hole ends in a singularity, a place where the laws of physics break down. But as we've discussed, singularities signal the failure of general relativity. When you have quantum scale densities, you need quantum gravity, and we don't yet know what quantum gravity predicts for the interior of black holes. Various approaches to quantum gravity suggest that singularities might be avoided. The infinite compression might stop at some extremely high but finite density, and then bounce back, beginning an expansion. Smolin proposed that this bounce creates a new region of space-time, a new universe, connected to the parent universe through the black hole, but causally disconnected from it. From the parent universe's perspective, the black hole is just a black hole, with matter falling in and nothing coming out. But from the perspective of the matter inside, after it's compressed to extremely high densities, it begins expanding again. The singularity is replaced by a bounce, and the other side of the bounce is a new expanding universe with its own Big Bang. If this happens, then every black hole is a doorway to a new universe. And in our universe, we're constantly making black holes. Massive stars collapse into black holes. Galaxies merge, and their central black holes coalesce. Every time this happens, in Smolin's model, a new universe is born. That new universe will have its own stars, its own galaxies, and its own black holes, each of which spawns another universe. This creates a vast branching tree of universes, a cosmic genealogy where universes reproduce through black holes. But Smolin went further. He suggested that the laws of physics might change slightly when passing through a black hole, bounce into a new universe. Not radically, the new universe still has to be stable and capable of forming structures, but the values of fundamental constants might shift a bit. One universe might have a slightly stronger strong nuclear force, another might have a slightly different electron mass. These small changes would affect the kinds of structures that form in the new universe, and critically, they would affect how many black holes form. If the constants are tuned such that lots of stars form, and many of them are massive enough to become black holes, that universe will have many black hole offspring. If the constants prevent star formation or make black holes rare, that universe will have few offspring. Over cosmic timescales, spanning vast numbers of generations, this creates a selection pressure. Universes that are good at making black holes have more offspring, and those offspring inherit similar physics. Universes that are bad at making black holes are evolutionary dead ends. This is natural selection applied to cosmology. The universes that exist are predominantly the descendants of universes that were good at reproducing, which means they're universes with physics that allows lots of black holes to form. And here's the fascinating part. The physics required to make lots of black holes overlap significantly with the physics required to make life. You need long-lived stars to forge heavy elements in their cores. You need stable atoms and molecules to build complex chemistry. You need a universe that's not too chaotic but not too boring, with structure formation that creates galaxies, stars, and planets. Smolin argued that cosmological natural selection might explain why our universe seems fine-tuned for life. It's not that the universe was designed for us, and it's not blind luck that the constants happen to have values compatible with life. Rather, we exist in a universe descended from a long line of black hole-producing ancestor universes. And the physics that produces lots of black holes also, as a side effect, produces conditions suitable for life. We're here because our universe is optimized for black hole production, and life is a byproduct of that optimization. You can probably see how cosmological natural selection connects to the idea that we might be inside a black hole. If every black hole creates a new universe, then every universe, including ours, is by definition inside a black hole. Our Big Bang would be the bounce that occurred inside a black hole in some parent universe. Our expansion is the expansion of this new universe growing inside the black hole. And every black hole we create spawns a child universe inside it, continuing the reproductive cycle. This gives the universe inside a black hole hypothesis more structure and potentially more explanatory power. Instead of just saying, maybe we're in a black hole with no reason to believe it, cosmological natural selection provides a mechanism and makes predictions. It predicts that the constants of physics should be near optimal for black hole production. It predicts that small changes to the constants should generally reduce black hole formation. These are testable predictions, at least in principle, though testing them is extraordinarily difficult given that we can only observe one universe. There are significant objections to cosmological natural selection. For one, it requires that singularities don't form, that quantum gravity resolves them into bounces, and we don't know if this is true. Different approaches to quantum gravity make different predictions, and we have no experimental data to guide us. Second, it's not clear that the constants really are optimized for black hole production. Some physicists have analyzed this and found that certain changes to the constants would increase black hole formation, not decrease it. Third, the idea is very difficult to test rigorously. We can't create black holes in the lab and check if universes form inside them. We can't compare our universe to other universes to see if we're typical of a population that evolved through natural selection. But even if cosmological natural selection is wrong, it illustrates an important point. The idea that our universe might be inside a black hole becomes more scientifically interesting if it's part of a larger framework that explains other features of our universe. If it's just an isolated what if, then it's curious, but not particularly valuable. If it's part of a theory that makes predictions and solves problems, then it's worth taking more seriously, even if those predictions are hard to test. Part 8. Observational challenges. The biggest problem with the hypothesis that we're inside a black hole is that it's very difficult, perhaps impossible, to test. Good scientific hypotheses make predictions that can be verified or falsified through observation or experiment. They have consequences that differ from alternative hypotheses in ways we can measure. But the claim that our universe is the interior of a black hole in some larger parent universe makes no obvious predictions that differ from standard cosmology. Think about what we can observe. We see an expanding universe with a Big Bang in the past. We see matter and energy distributed nearly uniformly on large scales. We see a cosmological event horizon beyond which we can't observe. All of these features are explained by standard cosmology using the FLRW metric and the assumption that our universe is all there is. The black hole hypothesis explains these same features by saying the FLRW metric describes the interior of a black hole rather than a standalone universe. But from our perspective inside, the mathematics is identical. The observations are identical. There's no difference to measure. Could we detect the event horizon of the black hole we're supposedly inside? In principle, if it were within our observable universe, we could potentially detect it as a boundary beyond which the expansion behaves differently or where the homogeneity breaks down. But if the black hole is large enough, orders of magnitude larger than our observable universe, then its event horizon is far beyond what we can see. We're like microbes living inside a single cell of a whale, trying to deduce the whale's existence. The structure we're embedded in is so much larger than what we can observe that we have no hope of detecting it directly. What about looking for signatures of the parent universe? Could radiation or information leak through from outside? In standard black hole physics, nothing can cross the event horizon from outside to inside in a way that would reach us. The event horizon is a one-way boundary. Information from the exterior universe cannot influence the interior. Even if the parent universe is doing wild things, sending signals, shining lights, those signals stop at the event horizon. They might hover there from the parent universe's perspective, redshifted to infinity, but they never cross over to reach us. There are some speculative ideas about quantum effects at event horizons that might allow information transfer, but these are highly uncertain and depend on the correct theory of quantum gravity, which we don't have. Hawking radiation is sometimes thought to encode information about the black hole's interior, but extracting that information would require observing the entirety of the Hawking radiation over the black hole's lifetime, which is impossible if you're inside the black hole. And even if information could somehow leak through, we'd need to distinguish it from all the other signals in our universe. An extraordinarily difficult task. There's another observational challenge related to cosmic inflation. The current standard model of cosmology includes a period of rapid exponential expansion in the universe's first fraction of a second, called inflation. This inflation is invoked to solve several problems in cosmology, including why the universe is so homogeneous and flat, and why we don't see certain exotic relics like magnetic monopoles that should have been produced in the early universe. Inflation is thought to have occurred at incredibly high energies, close to the scale where quantum gravity effects become important. If our universe is inside a black hole, and if that black hole formed through stellar collapse in a parent universe, then the matter inside had to pass through a phase of extreme compression. The Oppenheimer-Snyder model assumes this happens smoothly, with matter remaining homogeneous. But real matter has pressure, temperature, and quantum properties that might affect the collapse and subsequent bounce if cosmological natural selection is correct. It's not clear how inflation would fit into a black hole cosmology scenario. Would inflation occur after the bounce? Would it occur before the collapse in the parent universe? Would the expansion of space inside the black hole naturally lead to inflation-like behavior? These questions don't have clear answers, and until they do, it's hard to reconcile black hole cosmology with our observational evidence for inflation. This doesn't necessarily rule out the hypothesis, but it does mean there's work to be done in developing a complete, consistent model that matches all our observations. One argument that's sometimes made in favor of multiverse scenarios, including scenarios where universes form inside black holes, is that they can potentially explain fine-tuning. Our universe appears to have fundamental constants and initial conditions that are remarkably well suited for the existence of complex structures and life. Change the strength of the strong nuclear force by a few percent, and stars can't forge carbon. Change the cosmological constant by much, and the universe either collapses before stars form or expands so fast that galaxies never coalesce. There are dozens of these apparent fine-tunings. One explanation is design. The constants were set by some intelligence to allow for life. Another is blind luck. We just happen to live in the one universe that exists, and it just happens to have the right properties. A third explanation is the anthropic principle combined with a multiverse. There are many universes with different constants, and we necessarily find ourselves in one that allows for our existence, not because it's special, but because we couldn't exist in the others to wonder about it. If black holes create new universes with slightly different constants, as in cosmological natural selection, or if there's a parent universe that creates black holes with various properties, then we have a natural multiverse scenario. The fine-tuning is explained not by design or luck, but by selection. We exist in a universe from a region of the multiverse where the constants allow for complex structures. This is an appealing explanation to many physicists because it doesn't require any special initial state for the universe as a whole, just a mechanism for variation and selection. However, this argument has weaknesses. First, we don't know if the constants can actually vary. They might be fixed by some deeper theory we haven't discovered yet. Second, even if they can vary, we don't know the probability distribution of different values. Maybe the values we observe are actually the most likely ones, and no anthropic reasoning is needed. Third, the anthropic principle is philosophically contentious. Some argue it's a cop-out, explaining away fine-tuning by appealing to unobservable other universes. Others argue it's the only reasonable explanation if a multiverse exists. The bottom line is that while black hole cosmology can provide a framework for anthropic explanations of fine-tuning, this doesn't constitute evidence for the hypothesis. It's a possible benefit if the hypothesis is true, but it's not a reason to believe the hypothesis is true. Part 9. Philosophical implications. Let's suppose, purely for the sake of argument, that we really are inside a black hole. What would this mean? How would it change our understanding of reality, our place in the cosmos, and the ultimate fate of everything we know? On one level, it might not mean much at all. From our perspective, nothing changes. We still observe an expanding universe with galaxies, stars, and planets. The laws of physics we've discovered still work exactly as they always have. Our immediate environment is unchanged. Learning that we're inside a black hole would be like learning that our planet orbits a star that's part of a galaxy, that's part of a supercluster. It's a change in context, in how we understand our place in the larger structure, but it doesn't affect our daily experience. On another level, though, it would be profound. It would mean that our entire observable universe, everything we can see or will ever see, is just the interior of a single object in a larger cosmos. It would mean there's a parent universe out there, forever inaccessible to us, whose properties and history gave rise to our universe. Are there intelligent beings in that parent universe? Did they somehow trigger the collapse that created the black hole we inhabit? These questions would be deeply interesting but forever unanswerable, since we can't observe or communicate with the parent universe. It would also change our understanding of the ultimate fate of our universe. In standard cosmology, with a positive cosmological constant, dark energy, the universe will continue expanding forever, accelerating as it goes. Eventually, in trillions of years, the expansion will have carried galaxies so far apart that they're all beyond each. Others event horizons, stars will burn out, black holes will evaporate via Hawking radiation, and the universe will approach a cold, dark, empty state called heat death. This is a depressing prospect, but it's what the equations predict if dark energy remains constant. If we're inside a black hole, the ultimate fate is different. Remember, the black hole singularity is a future space-like singularity. All geodesics inside the black hole terminate at the singularity in the future. This would suggest that our universe is doomed to collapse back down to infinite density at some point. But this contradicts what we observe, which is accelerating expansion, not contraction. How do we reconcile this? One possibility is that the interior of the black hole is so large and the singularity is so far in the future that we simply haven't reached the phase of collapse yet. We're in the expanding phase, which from the interior looks like it might continue forever, but eventually the expansion will reverse and will contract back toward the singularity. Another possibility is that the black hole is in an equilibrium state, as Hawking suggested, and the singularity is somehow avoided or indefinitely postponed. A third possibility is that our understanding of black hole interiors needs revision once quantum gravity is included, and the singularity doesn't work the way classical general relativity predicts. These questions remain open, and they highlight a key point. The hypothesis that we're in a black hole raises more questions than it answers. Without a complete theory of quantum gravity, without a way to test the hypothesis observationally, we're left with interesting speculation, but no definitive conclusions. There's also a question about cosmic significance. Humans have a long history of thinking we're at the center of everything, only to be repeatedly shown that we're not. We thought Earth was the center of the universe, but it's just one planet among many. We thought the Sun was special, but it's an ordinary star in an ordinary galaxy. We thought our galaxy was the entire universe, but it's one of hundreds of billions of galaxies. Each step has been a humbling revision downward of our cosmic importance. If we're inside a black hole, it's another such revision. Not only is our universe not all there is, but our entire universe is just the interior of a single object in a much larger structure. We're not even living in the real universe, the parent universe where black holes form and stars shine and beings might look at our black hole from the outside. We're inside, cut off, isolated, forever unable to interact with or even observe the larger reality. From the perspective of the parent universe, we might not even be considered real or significant. We're just the interior of a black hole, a region of space-time that's interesting mathematically but causally disconnected from the rest of reality. This is a bit of a gloomy perspective, but it's also liberating in a way. If we're inside a black hole, then nothing we do can affect the parent universe. We're completely self-contained. Our actions, our achievements, our failures, all of human history and all of cosmic history within our universe, it all unfolds in isolation. We're not part of some larger story being written in the parent universe. We're our own story, playing out in our own bubble of space-time. This gives a certain freedom and autonomy to our existence, even as it emphasizes our isolation. On the other hand, if cosmological natural selection is correct, then we're part of a vast genealogy of universes, connected through a process of cosmic reproduction. Our universe had parents, grandparents, deep ancestry stretching back through countless generations. And every black hole we create is a child universe carrying forward the cosmic lineage. This is a very different perspective, one that embeds us in a larger process, even if we can't interact with our cosmic relatives. We're part of the tree of universes, one branch among countless others, but a branch nonetheless. Perhaps the most profound philosophical implication is about the limits of knowledge. One of the great aspirations of physics is to understand everything, to develop a theory of everything that explains all phenomena in the universe from the smallest quantum scales to the largest cosmic scales. We want to know how the universe began, how it will end, and why it has the properties it does. But if we're inside a black hole, there are fundamental limits to what we can know. We can never observe the parent universe. We can never test hypotheses about how our black hole formed or what's happening outside. We can never know if there are other universes or if we're truly alone. These aren't limitations of technology or ingenuity. They're fundamental limitations imposed by the causal structure of space-time. Information from outside the event horizon simply cannot reach us. No amount of cleverness will overcome this barrier. This is simultaneously frustrating and fascinating. It's frustrating because it means there are questions we might never answer, mysteries that will remain forever beyond our reach. But it's fascinating because it reveals something deep about the structure of reality. The universe doesn't owe us complete knowledge. There can be aspects of reality that are real, that exist, that have effects, but that are nevertheless fundamentally unobservable to us. This challenges our intuitions about what it means for something to exist and what role observation and measurement play in defining reality. In quantum mechanics, we're already familiar with the idea that observation plays a special role. Unobserved quantum systems exist in superpositions of states, and observation collapses them into definite states, at least according to some interpretations. But that's about the act of observation changing the system. The black hole scenario is different. It's about the existence of things that cannot even in principle be observed, not because observing them would change them, but because the causal structure of space-time prevents any interaction. This has implications for how we do science. If there are real aspects of the universe that cannot be observed, how do we incorporate them into our scientific worldview? Do we simply ignore them as irrelevant? Do we acknowledge their possible existence but refuse to speculate about them? Do we develop theoretical frameworks that include them even though we can't test those aspects directly? Different scientists will answer differently, and these answers reflect different philosophies of science. Some physicists are comfortable with theories that make unobservable predictions as long as the observable predictions are correct and the theory is elegant and explanatory. Others insist that scientific theories should only include elements that can be tested, and anything unobservable should be discarded as metaphysics rather than physics. The debate about multiverses and the landscape of string theory solutions has brought these philosophical differences to the forefront in recent years, and the question of whether we're in a black hole touches on similar issues. Part 10. Alternative perspectives. The hypothesis that we're inside a black hole is not the only speculative idea about the origin and nature of our universe. Theoretical physics has produced a rich variety of scenarios, each attempting to explain features of our universe that seem mysterious or fine-tuned. It's worth briefly surveying some of these alternatives to see how the black hole hypothesis compares. One popular idea is eternal inflation, where the inflation that occurred in our universe's early moments is just one bubble in an eternally inflating multiverse. In this scenario, inflation never completely ends. It's always happening somewhere. Occasionally, regions of inflating space undergo a transition to a non-inflating state, and these regions become pocket universes like ours. Each pocket universe can have different properties, different constants of nature, depending on the details of how the transition occurred. This creates a vast multiverse of bubble universes, each with its own Big Bang, but all embedded in the larger, eternally inflating structure. Eternal inflation has some nice features. It explains why our universe seems so unlikely, why the constants are fine-tuned for life. If there are countless bubble universes with different properties, of course we find ourselves in one that allows for our existence. It also potentially explains the initial conditions for inflation in our universe, since those conditions are just the random quantum fluctuations in the larger inflating space-time. But it also has problems. The eternally inflating multiverse is extremely difficult to analyze mathematically, and it's not clear how to make probabilistic predictions about what typical observers should expect to see. Also, like the black hole hypothesis, the other bubble universes are unobservable, raising questions about whether this is science or speculation. Another idea is the cyclic or ekpyrotic universe, where our universe goes through repeated cycles of expansion and contraction. The Big Bang is not the absolute beginning, but rather the latest in a series of bounces where the universe contracted down to very high density and then bounced back into an expansion. This could potentially avoid the initial singularity problem and explain why the universe is so homogeneous, since the previous cycle could have smoothed out inhomogeneities. There are different versions of cyclic models. some involving just our universe cycling endlessly, others involving the collision of higher dimensional brains in string theory. These models have their own challenges, including stability issues and questions about how information is lost or preserved across cycles. There's also the quantum cosmology approach, where the universe is treated as a quantum object and its origin is described by a quantum wave function rather than a classical space-time. In this framework, championed by people like Stephen Hawking and James Hartle, the Big Bang singularity is smoothed out by quantum effects, and the question, what came before the Big Bang, becomes meaningless because time itself emerges from the quantum state. The universe doesn't have a beginning in time. It has a boundary condition in imaginary time, which is a mathematical trick that avoids the singularity. This is deeply abstract and difficult to interpret, but it represents an attempt to apply quantum mechanics to cosmology in a fundamental way. How does the black hole hypothesis compare to these alternatives? In terms of mathematical rigor and development, it's probably less developed than eternal inflation or quantum cosmology, which have been studied extensively by many researchers over decades. The black hole cosmology idea has had fewer champions and less detailed technical development. But it has the advantage of being based entirely on standard general relativity, without requiring speculative additions like eternal inflation fields or quantum cosmology wave functions. In terms of testability, all of these ideas face similar challenges. They all make predictions about regions or epochs that are beyond our observational reach. The other bubble universes in eternal inflation are unobservable. The previous cycles in a cyclic universe are unobservable. The quantum state that gave rise to our universe in quantum cosmology is not directly observable, and the parent universe outside our black hole is unobservable. So the black hole hypothesis is not uniquely problematic in this regard. It's part of a broader landscape of speculative cosmological ideas that push beyond what we can directly test. Where the black hole hypothesis might have an advantage is in its conceptual simplicity. It doesn't require new physics beyond general relativity, though it does require understanding what happens at singularities, which needs quantum gravity. It doesn't require fine-tuning of initial conditions, since those conditions could be set by the collapse in the parent universe. And it provides a natural explanation for both the Big Bang singularity and the cosmological event horizon in one framework. Of course, simplicity alone doesn't make an idea correct, but it's a virtue when comparing speculative hypotheses that all lack direct evidence. Many of these speculative cosmological ideas, including the black hole hypothesis, ultimately depend on having a correct theory of quantum gravity. String theory is currently the most developed approach, though it's far from complete or experimentally verified. String theory has some interesting things to say about black holes and cosmology that are relevant to our discussion. In string theory, everything is made of tiny vibrating strings rather than point particles. Different vibration modes correspond to different particles. One of the great successes of string theory is that it naturally includes gravity. One of the vibration modes of strings corresponds to the graviton, the hypothetical particle that would mediate the gravitational force if gravity were quantized like other forces. This means string theory is automatically a theory of quantum gravity, though we don't yet know how to extract testable predictions from it in most situations. String theory has led to some fascinating insights about black holes. String theorists have been able to calculate the entropy of certain black holes by counting the number of microscopic string states corresponding to the black hole macroscopic properties. This entropy matches the Bekenstein-Hawking entropy predicted by semi-classical gravity, which is a remarkable consistency check. String theory also suggests that singularities might be resolved by stringy effects. with the infinite curvature at the singularity being smoothed out at the string scale. There are also string cosmology scenarios where the universe emerged from a pre-Big Bang state, possibly involving higher dimensional spaces that underwent dimensional reduction to give us our familiar four-dimensional space-time. Some of these scenarios have features similar to the black hole hypothesis, with the universe emerging from a highly curved, high-density state that might be described as the interior of a higher dimensional black hole. But these ideas are very preliminary and highly speculative even by the standards of string theory. Loop quantum gravity, an alternative approach to quantum gravity, also has things to say about singularities. Loop quantum gravity suggests that space is fundamentally discrete at the Planck scale, made up of tiny quantum chunks. When matter collapses toward a black hole singularity or toward the Big Bang, loop quantum gravity predicts that quantum effects halt the collapse at extremely high but finite densities. The singularity is replaced by a bounce, very much as required by cosmological natural selection. Loop quantum cosmology, applying these ideas to the early universe, has been studied in detail and suggests that the Big Bang might have been a big bounce from a previous contracting phase. The point is that different approaches to quantum gravity give different predictions about what happens at singularities, and these predictions matter for whether the black hole cosmology hypothesis makes sense. If singularities are truly singular, truly places where physics breaks down completely, then it's hard to understand how a coherent universe could emerge from one. But if quantum gravity resolves singularities into bounces or high-density but non-singular states, then the transition from a collapsing black hole to an expanding universe becomes more plausible. We won't know which approach is correct until we have experimental evidence for quantum gravity, which might require energies far beyond what we can achieve in particle accelerators. Observations of the cosmic microwave background or gravitational waves from the early universe might provide indirect evidence, but these windows on quantum gravity are limited. We might have to wait a long time for definitive answers. Part 11. The mathematics of black hole spacetimes. To really understand the black hole hypothesis, we need to dig a bit deeper into the mathematics of black hole spacetimes. The simplest black hole solution is the Schwarzschild metric, discovered by Carl Schwarzschild in 1916, just months after Einstein published general relativity. Schwarzschild was serving in the German army during World War I when he found this exact solution to Einstein's equations. Sadly, he died shortly after from an illness contracted during the war, but his solution has been central to our understanding of gravity ever since. The Schwarzschild solution describes a perfectly spherical, non-rotating, electrically neutral black hole that has existed for all eternity. It's not a realistic black hole, since real black holes form from stellar collapse and rotate, but it captures the essential features. The metric has two key components, the radial coordinate and the time coordinate. Far from the black hole, the metric approaches flat space-time, confirming that the solution describes an isolated object. Near the black hole, the metric becomes increasingly curved. At a special radius called the Schwarzschild radius, something strange happens in the coordinate system. The time and radial coordinates appear to switch roles. This is the event horizon, and the coordinate singularity here confused physicists for decades. People thought the event horizon was a real physical singularity where something catastrophic happened. It wasn't until the 1960s that physicists clearly understood that the singularity in the Schwarzschild coordinates was just an artifact of a bad choice of coordinates, like the apparent singularity at the North Pole when using latitude and longitude. Choose better coordinates and the horizon is perfectly smooth. Inside the horizon, the Schwarzschild metric predicts that the singularity at the center is unavoidable. All time-like paths, All possible trajectories of anything that crosses the horizon lead to the singularity in finite proper time. The singularity is at r equals 0 in the Schwarzschild coordinates. But this isn't really a location in space. It's a moment in time, a space-like surface in the future of anything inside the horizon. This is hard to visualize because our normal intuitions about space and time don't apply inside the horizon. Physicists have developed various coordinate systems and diagrams to visualize black hole spacetimes. Penrose diagrams are particularly useful. They compress the entire infinite spacetime onto a finite diagram, with light rays always traveling at 45-degree angles. In a Penrose diagram, you can clearly see the causal structure. What regions can influence what other regions, where the horizons are, where the singularities appear. For the Schwarzschild black hole, the diagram shows the exterior universe, the interior of the black hole, and the singularity as a space-like boundary at the top of the diagram. When you extend the Schwarzschild solution as far as possible, maximally extending it to include all possible geodesics, you get a surprising structure. The complete spacetime includes not just the black hole and the exterior universe, but also a white hole and a second exterior universe. These four regions are connected through the black hole interior in a way that creates a kind of bridge or wormhole, though not a traversable one. The white hole region is the time reverse of the black hole. Where the black hole has a future singularity that everything inside reaches, the white hole has a past singularity that everything inside emerged from. The white hole's event horizon can only be crossed from inside to outside, the opposite of the black hole. The two exterior universes are causally disconnected from each other. Light or matter from one exterior region can fall through the black hole, but they end at the singularity before they can reach the other exterior region. This maximally extended Schwarzschild spacetime is beautiful mathematically, but probably not physically realistic. It requires the black hole to have existed eternally, with no formation process, and it requires very special symmetry. Real black holes form from stellar collapse and don't have the white hole region or the second exterior universe. But the maximal extension is useful for understanding the general structure of solutions and for thinking about white holes as mathematical objects. When you apply similar maximal extension techniques to rotating black holes, described by the Kerr metric, you get even weirder structures. The Kerr black hole has an inner horizon, in addition to the outer event horizon, and the region inside the inner horizon contains closed time-like curves, paths through space-time that loop back on themselves in time. This allows for time travel, at least in principle, though most physicists believe these features are unstable or unphysical. Still, they're there in the mathematics, showing how rich and strange the solutions to Einstein's equations can be. The point of discussing these mathematical structures is to show that general relativity allows for incredibly complex and counterintuitive space-time geometries. Black holes, white holes, wormholes, closed time-like curves, these are all valid solutions to the equations. Whether they exist in nature is a separate question, but they're mathematically consistent. This gives us some confidence that the idea of a universe inside a black hole, while strange, is at least mathematically possible within general relativity. For the Oppenheimer-Snyder solution and related models where you patch a cosmological metric inside a black hole, the key is matching the metrics at the boundary. The boundary is the surface of the collapsing star, or, in the time-reversed case, the surface of the expanding matter distribution. Outside this surface, you use the Schwarzschild metric, or a similar exterior solution. Inside, you use an FLRW metric. The FLRW metric has its own structure. It describes a homogeneous, isotropic spacetime with a scale factor that changes with time. When the scale factor is increasing, space is expanding. When it's decreasing, space is contracting. The expansion or contraction is driven by the matter and energy content through the Friedmann equations, which relate the rate of change of the scale factor to the density and pressure of matter. For a flat FLRW universe, which is approximately what we observe, the spatial geometry is Euclidean. Space is flat, not curved, even though space-time as a whole is curved because of the time dependence of the scale factor. This flatness is why we can use ordinary geometry to measure distances and angles on cosmic scales, at least locally. The curvature of space-time shows up in the expansion and in gravitational effects, but not in the spatial geometry itself. When you put an FLRW metric inside an Oppenheimer-Snyder black hole, the matching at the boundary requires some careful mathematics. You have to ensure that the metric is continuous across the boundary and that it satisfies the Einstein equations everywhere. This is possible for the specific case of a uniform, pressureless dust cloud, which is what Oppenheimer and Snyder considered. For more realistic matter with pressure gradients and non-uniform density, the matching is more complicated and might not be possible in a simple closed form. This raises a question. Is the Oppenheimer-Snyder solution realistic enough to base cosmological speculation on? Real stars aren't uniform pressureless dust. They have complex structure, nuclear reactions, magnetic fields, and turbulence. When they collapse, the collapse is not perfectly spherical or uniform. Does the FLRW interior survive when you make the model more realistic? The answer is probably not exactly, but it might survive approximately if the deviations from homogeneity are small. For cosmological natural selection or Path3's black hole cosmology to work, you don't need perfect homogeneity. You need approximate homogeneity, enough that observers inside see a nearly uniform universe. Small inhomogeneities are actually necessary to seed the formation of structure like galaxies and stars. So the question is whether the collapse process in the parent universe can produce an interior that's homogeneous enough to look like our universe. This is an open question that probably requires detailed numerical simulations to answer, and such simulations are very challenging given the complexity of the physics involved. Part 12. The Observational Universe. Let's take a step back from the theoretical speculation and focus on what we actually observe about our universe. We have an enormous amount of data from telescopes, satellites, and experiments that tell us about the universe's properties, and any hypothesis about the nature of our universe needs to be consistent with all of this data. So what do we see? We see that the universe is expanding. Galaxies are moving away from us, and the farther they are, the faster they're receding. This was discovered by Edwin Hubble in the 1920s and has been confirmed and refined by countless subsequent observations. The expansion rate, the Hubble constant, is currently about 70 kilometers per second per megaparsec, meaning that a galaxy 1 megaparsec away is receding at 70 kilometers per second, a galaxy 2 megaparsecs away at 140 kilometers per second, and so on. There's actually a controversy in cosmology right now because different measurement methods give slightly different values for the Hubble constant, but all agree that the universe is expanding. We see the cosmic microwave background, the afterglow of the Big Bang. This radiation fills all of space and has a nearly perfect thermal spectrum with a temperature of 2.725 Kelvin. The tiny temperature variations across the sky, measured to exquisite precision by satellites like WMAP and Planck, tell us about the density fluctuations in the early universe that seeded the formation of cosmic structure. The statistical properties of these fluctuations match the predictions of inflation and tell us about the physics of the early universe when it was less than a second old. We see the large-scale structure of the universe, galaxies arranged in filaments and walls surrounding vast voids like a cosmic foam. This structure grew from the tiny density fluctuations in the early universe through gravitational amplification. Dense regions got denser, pulling in more matter, eventually forming galaxies and galaxy clusters. The distribution of this structure tells us about the total matter content of the universe and the relative amounts of ordinary matter, dark matter, and dark energy. We see that the expansion of the universe is accelerating. Observations of distant supernovae in the late 1990s showed that the universe is not just expanding, but expanding faster and faster. This acceleration is attributed to dark energy, a mysterious component that makes up about 68% of the energy content of the universe. Dark energy has negative pressure, which drives accelerated expansion according to Einstein's equations. We don't understand what dark energy is, whether it's a cosmological constant, a new field, or something else entirely, but we can observe its effects clearly. We see that the universe is very close to spatially flat. The angles in cosmic triangles add up to 180 degrees, just as in Euclidean geometry. This means the large-scale spatial geometry of the universe has zero or very nearly zero curvature. This is the flatness problem. Why is the universe so flat when almost any initial conditions would lead to significant curvature by now? Inflation provides one explanation, but it's still a mystery. We see that the universe is very homogeneous and isotropic on large scales. Look in any direction, far enough out, and you see roughly the same distribution of galaxies, the same average density, the same cosmic microwave background temperature. There are local variations, of course, but averaged over scales of hundreds of millions of light years, the universe looks the same everywhere. This is consistent with the cosmological principle, the assumption that we're not in a special location. All of these observations constrain any alternative cosmological model, including the black hole hypothesis. If we're inside a black hole, the interior has to be homogeneous and isotropic to match what we see. It has to be flat or very nearly flat. It has to be expanding at the observed rate with the observed acceleration. The cosmic microwave background has to be explained, with its thermal spectrum and its fluctuations. The formation of structure has to work the same way. For the Oppenheimer-Snyder type models, many of these requirements are naturally satisfied. The FLRW metric inside the black hole is by construction homogeneous and isotropic. It can be flat, which corresponds to a specific relationship between the matter density and the expansion rate. The expansion emerges naturally from the metric, but what about the cosmic microwave background? In standard cosmology, the CMB is radiation left over from the hot, dense early universe, released when atoms formed and the universe became transparent. Does this make sense inside a black hole? If the black hole formed from the collapse of matter in the parent universe, and if that matter was initially hot and dense, then yes, there could be a radiation-dominated phase after the bounce that looks like the early universe in standard cosmology. As the interior expands, the radiation cools and eventually matter dominates, just as in standard cosmology. The CMB would be the cooled radiation from this early hot phase. The details depend on the physics of the bounce and the initial conditions, which we don't fully understand, but in principle it could work. What about dark energy and the accelerating expansion? This is trickier. In standard cosmology, dark energy is often modeled as a cosmological constant, a form of energy that doesn't dilute as the universe expands. In general relativity, a cosmological constant is equivalent to a curvature of space-time that doesn't depend on the matter or energy content. It's a property of the vacuum itself. Could there be a cosmological constant inside a black hole? There's no obvious reason why not. The cosmological constant is a term that can be added to Einstein's equations, and it would affect the expansion inside the black hole just as it does in standard cosmology. Alternatively, dark energy might be something more exotic, like quintessence, a dynamical field that varies over time. If that's the case, the behavior of dark energy inside the black hole would depend on the properties of the field and how it couples to matter and gravity. Again, there's no fundamental reason this couldn't exist inside a black hole interior, but we don't have a detailed model to compare to observations. The bottom line is that the black hole hypothesis is consistent with many of our observations, at least at a qualitative level. But we don't have a sufficiently detailed model to make quantitative predictions that could be tested against the precision data we have. This is one of the main weaknesses of the hypothesis. It's a plausible idea, but it's not developed enough to be a true competitor to standard cosmology. Part 13. The Singularity Resolution Problem. Singularities represent the deepest failure of general relativity points where space-time curvature grows without bound, and the laws of physics lose their meaning. When a singularity forms, geodesics simply end, predictability vanishes, and determinism breaks down. Most physicists interpret this not as a real physical feature of the universe, but as a clear sign that general relativity is incomplete. A more fundamental theory, most likely quantum gravity, is expected to remove these infinities. Several approaches support this idea. Loop quantum gravity proposes that space-time has a discrete structure at the smallest scales, preventing infinite density and replacing singularities with bounces. String theory avoids singularities by replacing point particles with tiny vibrating strings, whose spatial extent smooths out extreme curvature. Other quantum gravity models also suggest mechanisms that prevent actual infinities, implying that inside black holes, collapse might transition into expansion rather than ending abruptly. If singularities are resolved this way, it opens the door to black hole cosmology, the idea that the interior of a black hole could become a new, expanding universe with its own space-time, separate from the parent universe. In this picture, our own Big Bang might not have been the absolute beginning, but a bounce from a prior collapsing phase, or the birth of our cosmos inside a larger universe. This interpretation also ties into the information paradox. General relativity suggests information disappears in black holes, while quantum mechanics forbids such loss. The AD-CFT correspondence and other holographic ideas indicate that information is preserved, albeit encoded in highly scrambled ways. If our universe originated inside a black hole, then information about a parent universe might be embedded in our own, though deeply disguised. Thinking of the universe as a black hole interior also affects how we imagine its long-term fate. Classical black holes have future singularities, which would correspond to a cosmic end, a type of far future Big Crunch. This seems at odds with the observed accelerating expansion driven by dark energy, but the acceleration may not last forever. Dark energy could evolve, weaken, or even reverse, allowing gravity to dominate again and trigger eventual contraction. Alternatively, quantum gravity might again replace the final singularity with a bounce, leading to yet another universe forming beyond ours. In this framework, every black hole could potentially spawn a new universe. This raises speculative but intriguing possibilities. Advanced civilizations might influence black hole formation in their own universe, indirectly shaping the properties of future universes born from those black holes. This idea, sometimes called cosmological natural selection, suggests a kind of evolutionary process across generations of universes, though it remains purely theoretical. while many aspects of this topic are grounded in solid science. Black holes, the cosmic microwave background, cosmic expansion, and gravitational physics. Much of the interior structure of black holes, quantum gravity, and the details of the early universe remain uncertain. The notion that our universe itself is the interior of a black hole is mathematically consistent in some models, but far from proven. At present, it cannot be directly tested with our available technology. But speculative ideas like this are not wasted effort. They drive scientific creativity and open new lines of inquiry. Historically, speculation has often led to breakthroughs, even if the original idea was wrong or incomplete. This hypothesis also intersects with major unresolved questions: the nature of time, the meaning of entropy on cosmic scales, the structure of the multiverse, and whether information can ever truly be lost. Even if the idea remains forever untestable, thinking about it helps sharpen our understanding of what we know and what we still don't see. Einstein himself would have had mixed feelings. He gave us the very equations that allow for black holes, yet he doubted they could physically form. He famously resisted the probabilistic nature of quantum mechanics, yet his work set the stage for the quantum revolution. Throughout his life, he balanced mathematical beauty with philosophical discomfort. Many of the predictions derived from his equations: supermassive black holes, gravitational waves, an expanding universe. The cosmic microwave background were confirmed long after his death. He would likely approach black hole cosmology with both curiosity and skepticism. General relativity remains one of humanity's greatest intellectual achievements, but Einstein knew it was not the final word. A successful theory of quantum gravity will likely reshape our understanding of black holes and may finally reveal what truly happens inside them. Contemplating our universe as the interior of a black hole can stir powerful emotions: insignificance, isolation, or awe. Yet meaning does not depend on cosmic scale. It emerges from human experience, relationships, and creativity. Whether we live inside a black hole or not does not diminish our significance. Instead, the idea can be seen as adding a layer of mystery and wonder to existence. Humans are naturally drawn to hidden worlds and secret structures, and this hypothesis taps into that ancient fascination. But this same fascination also requires caution. Imagination must be balanced by skepticism, evidence, and the willingness to revise our beliefs. Testing this hypothesis is extraordinarily difficult. We would need to determine the true size and shape of the universe, search for repeating patterns in the cosmic microwave background that might indicate a specific global topology, or detect subtle imprints in gravitational waves and primordial fluctuations. These possibilities are intriguing, but they currently lie far beyond our observational and technological capabilities. For now, distinguishing black hole cosmology from standard cosmology remains an open challenge. In the end, the idea that our universe exists inside a black hole is a blend of cutting-edge physics and informed speculation. It cannot yet be confirmed or ruled out, but it expands the frontier of how we think about origins, boundaries, and the nature of reality itself. It pushes us to question what a universe really is, and whether ours is just one chapter in a much larger cosmic story. Conclusion. The verdict. After this deep dive into black holes, cosmology, quantum gravity, and the mathematical gymnastics required to contemplate universes within black holes, what's the answer? Are we living inside a black hole right now? The honest scientific answer is probably not, but not absolutely not. There's no good reason to believe that we are inside a black hole. The standard cosmological model, where our universe is a standalone entity described by the FLRW metric with a big bang in the past and ongoing expansion driven by dark energy, explains all our observations perfectly well. It doesn't require a parent universe or a black hole embedding. Occam's razor, the principle that we should prefer simpler explanations when they account for the data equally well, favors standard cosmology over black hole cosmology. Moreover, the black hole hypothesis is underdeveloped. While the basic idea that you can patch an FLRW metric inside a collapsing or expanding star is mathematically sound, extending this to a full cosmological model that explains all the details of our universe, the cosmic microwave background, dark energy, inflation, structure formation, all of that work hasn't been done in sufficient detail. Until someone develops a complete, quantitative model that makes testable predictions, the hypothesis remains more of an interesting observation than a serious contender. However, we cannot say with absolute certainty that we're not inside a black hole. The mathematics of general relativity allows for it. Nothing in our observations rules it out definitively. If the black hole is large enough and has the right properties, observers inside would see exactly what we see: an expanding, homogeneous universe with a big bang in the past. We would have no way to detect the difference between being in a black hole and being in a standalone universe. This is where the hypothesis rests: possible but not necessary, consistent but not compelling, intriguing but not established. It's a reminder that there are aspects of reality that might be forever beyond our ability to confirm, regions of the multiverse or layers of cosmic structure that we can reason about mathematically but never observe directly. This is both humbling and fascinating, a testament to how strange and surprising the universe revealed by modern physics really is. Even if we never answer the question definitively, there's value in having asked it. Thinking about whether we're inside a black hole forces us to confront deep questions about the nature of space-time, the origin of the universe, the limits of observability, and the relationship between mathematics and physical reality. It connects cosmology to black hole physics, quantum mechanics to general relativity, and fundamental physics to philosophy. The hypothesis has generated interesting ideas like cosmological natural selection, which tries to explain the apparent fine-tuning of physical constants through a process of cosmic evolution. Whether or not that specific idea is correct, it's an example of how speculative cosmology can suggest new frameworks for understanding why the universe has the properties it does. Thinking about black hole interiors and whether we might be in one also motivates work on quantum gravity. If we had a complete theory of quantum gravity, we could definitively say what happens at singularities, whether bounces occur, whether information is preserved, how black hole interiors behave. This would let us assess the black hole cosmology hypothesis much more rigorously. So in a sense, the hypothesis is a motivation for solving some of the deepest problems in theoretical physics. There's also pedagogical value. Explaining the black hole cosmology hypothesis requires explaining general relativity, cosmology, geodesics, singularities, event horizons, the difference between space-like and time-like, quantum gravity, and many other concepts. It's a great vehicle for teaching deep physics ideas because it connects them all in one narrative. Students learning about this hypothesis will come away with a richer understanding of modern physics than they would from studying each topic in isolation. Let's engage in one final thought experiment. Suppose future developments in quantum gravity and cosmology somehow definitively prove that we are inside a black hole in a parent universe. How should we react? What would this mean for humanity and our place in the cosmos? On a practical level, nothing would change. The laws of physics we've discovered would still work the same way. The technologies we've built would still function. The sun would still rise and set. Life would go on as before. The difference would be purely conceptual, a change in our cosmic context rather than our immediate experience. Philosophically and psychologically, the impact could be profound. It would be another Copernican revolution, another step in the journey from seeing ourselves as the center of everything to realizing we're a small part of something much larger. We're not just one planet among many, not just one star system among billions, not just one galaxy among trillions. Our entire universe would be one object among countless others in a larger reality we can never access. This could inspire humility and wonder. The universe is even more magnificent than we thought. There are levels of reality beyond what we can observe. Our isolation in our black hole bubble makes the connections we have with each other, the life and consciousness that has emerged in our small corner of existence, even more precious and meaningful. We're truly alone in our universe, or at least we can never confirm we're not, which makes our responsibility to preserve and cherish what we have all the greater. It might also inspire new questions. What is the parent universe like? Could it be fundamentally different from ours, with different constants of nature, different dimensions, different laws of physics? Are there intelligent beings in the parent universe? Did they somehow cause the collapse that created our black hole? These questions would be unanswerable, forever beyond our reach, but that wouldn't stop us from wondering and speculating. Humans have always wondered about what lies beyond our reach. If cosmological natural selection is correct, it would also change how we think about creating black holes. Every black hole we create or allow to form would be a new universe with the potential for its own stars, planets, and life. This would give cosmic significance to astrophysical processes and potentially to human actions if we ever gain the capability to influence black hole formation. We would be cosmic parents, creating offspring universes, though we'd never be able to meet our children or see what becomes of them. Ultimately, whether we're inside a black hole or not, whether we ever answer this question or not, there's something beautiful about the fact that we can ask it. We've developed mathematical languages and observational techniques sophisticated enough to contemplate the deepest questions about reality. We've built telescopes that can see billions of light years into space and billions of years into the past. We've detected gravitational waves, ripples in space-time itself. We've imaged the shadow of a black hole's event horizon. We've measured the temperature of the cosmic microwave background to 5 decimal places. And yet, with all this knowledge and capability, we still face profound mysteries. We still have questions we can't answer, or can't answer yet. This is not a failure of science, but a testament to the richness and depth of reality. The universe doesn't reveal all its secrets easily. Every answer opens new questions. Every mystery solved reveals deeper mysteries underneath. The question, are we inside a black hole, sits at the frontier of human knowledge, in that fuzzy region between what we know and what we might never know. It's an example of how science pushes boundaries, how mathematical reasoning can take us to places observation cannot, how theoretical physics explores possibilities that experiment may never confirm or deny. It's a reminder that reality is under no obligation to be fully comprehensible to us, that there may always be aspects of existence that remain beyond our grasp. And perhaps that's how it should be. A universe that was completely understood, where every question had been answered and no mysteries remained, might be a boring universe. The fact that we can still wonder, still speculate, still push the boundaries of knowledge into unknown territory, that's what makes the scientific enterprise exciting. Whether we're inside a black hole or not, we're inside a universe that continues to surprise and amaze us. A universe worth exploring for as long as we exist to explore it. So the next time you look up at the night sky, at the stars and galaxies scattered across the cosmic void, consider the possibility that all of it, every single thing you see, might be contained within the event horizon of a massive black hole in some larger parent universe. Consider that the Big Bang might have been the moment of formation of this black hole, that the expansion of space might be the expansion of the black hole's interior, that the cosmological horizon might be related to the black hole's event horizon. Consider that beyond our reach, in a realm we can never observe, there might be a larger reality of which we're just one small, isolated part. Or consider that we're alone, that our universe is all there is, that the Big Bang was the absolute beginning and there's nothing beyond or before or outside. That's equally mind-boggling in its own way. Either possibility confronts us with the strangeness and grandeur of existence. Whatever the truth turns out to be, we're privileged to live in an age when we can ask these questions seriously, when we have the tools to explore them mathematically and observationally, when we can push human knowledge to its limits and maybe a bit beyond. The universe has given us consciousness, curiosity, and the ability to understand, at least partially, the cosmos we inhabit. Whether we're in a black hole or not, that's extraordinary. And it's enough.